So this is the last thing we have to do on cellular respiration. All right, so the electron transport chain. What you need to remember, a summary of it is where those high energy electrons from our two carriers, NADH and FADH2, are passed along proteins. And those proteins are embedded in the inner mitochondrial membrane. When the electrons move through the proteins, the energy it creates is used to move hydrogen ions from the matrix into, bless you, the inner membrane space. So you guys saw it in your thing. There's a whole bunch of different proteins. And they're embedded in that membrane. And what it shows is those electrons, as they pass through, it's going to throw a hydrogen ion up. Passes through the next one, throw another hydrogen ion up. Pass through the next one, throw another hydrogen ion up. Then those electrons have got to go somewhere. So we have our electron sponge in the form of oxygen. The oxygen, when it collects all the electrons it can, is going to hook up with one of those hydrogen ions, and it's going to wait for another friend, and it's going to make water, and that's going to be released. The pumping of those ions into the inner membrane space is going to be potential energy. What is potential energy? Could be. What's potential energy? If I say you've got a lot of potential, what does that mean? You can do something. So what do you think potential energy is? Yeah, it's stored energy. So it represents potential energy. And that potential energy, you should know from physics. Potential energy based on position, right? What happens if we want to use potential energy? What does it become? Kinetic energy. So this potential energy here, so it's stored energy when we pump it across there. It turns into kinetic energy, which is the energy associated with its movement, as those hydrogen ions fall through the ATP synthase and make ATP. And that kinetic energy is transferred into the bond, that's now stored in the ATP. So the position of those hydrogen ions creating that gradient represents potential energy. It's just waiting there to be used. As soon as those hydrogen ions move through the ATP synthase, it's going to make ATP and it turns into kinetic energy. Remember that the oxygen is your final electron acceptor. It's going to be that electron sponge. And it forms H2O with 2 hydrogen ions. And this happens in the matrix after those hydrogen ions have fallen back through. All All right, so the electron transport chain is going to take place right here. It's going to be embedded here. Over here, you're going to see that those high energy electrons are being passed through those embedded proteins. Notice that the NADH has more potential energy. It passes through essentially 3 proteins, which means more hydrogen ions are pumped through, which means more ATP is made. So we said for each NADH, we can make 3 ATPs. Remember, your FADH2 is going to start much further down the line. So we end up with a high concentration of hydrogen ions here and a low concentration down here. What's going to happen? We have low here. It's going to diffuse through, and it's going to cause the ATP synthase. Your FADH2, here it is. It's going through, only goes through 2 proteins. If it goes through 2 proteins, it's going to move 2 hydrogen ions, which means it makes only 2 ATP. So it has less energy or potential energy than your NADH. But either way, it's going to pump those hydrogen ions up into the inner membrane space. They're going to wait and fall back through because of that simple diffusion, and you're going to make ATP. So the total yield for respiration, what do we end up making? Well, how about we do it by steps? Glycolysis. We made 4, 2 we get to keep. For Krebs, we get to keep 2 ATP. How many NADHs did we have in glycolysis? 2 NADHs in glycolysis. How many NADHs did we have in the Krebs cycle? 8 total. And we had 2 FADH2. So that's total here would be 10 times 3. So that's 30 ATP from our NADHs and 4 ATP from our FADH2s. So we end up with a total in a perfect world of 38 ATP. Almost nothing makes 38 ATP. The actual net yield that you end up with is somewhere around 32. So that's a pretty good system. 38 would be in a perfect world, in like Tony's world. But the rest of us mere mortals, we're only chucking out about 32 ATPs. One day, Tony, we'll be as good as you.
38 ATP.
Mm-hmm. So in eukaryotes, you're going to have glycolysis, to Krebs, to ETC. So you're looking at somewhere around 32 ATP. So again, here's that maximum yield in eukaryotes. In prokaryotes, what are they doing? Prokaryotes are doing glycolysis, but what else are they doing? They're mostly doing fermentation. Why?
Because they don't have mitochondria, so they were not able to do the moving phase.
Well, prokaryotes, they're going to get the 2 in glycolysis. Some prokaryotes are going to have have proteins on the inner surface of their outer membrane. So they can do a version for that more complicated cell respiration. But it's not going to be as great as the eukaryotic ones. The fact that they have similar proteins embedded on the inner side of their outer membrane, what does that kind of tell you? If they have proteins that allow for cell respiration embedded on their outer membrane, what does that kind of tell you? Where did the inner membrane of the mitochondria come from? It was the outer membrane of the original prokaryote, so it's just more proof for the endosymbiotic theory. Okay. In addition to glucose, there are other food molecules that can be used in cell respiration. Your body can break down fats, and it can also break down proteins if needed.